Hello again, Physics 30s. We are here today talking about Unit 5, that's Atomic Physics. We're on Lesson 8. Better double check that. I believe we're on Lesson 8. Yep. And it is all 100% about the Bohr model of the atom, and the whole reason that we have the Bohr model of the atom is because it is there to explain the atomic spectra of hydrogen. And that is it. Hydrogen. Cool. But that being said, it does explain the atomic spectra of hydrogen very, very well. But it also, when we extrapolate it a little bit, it also explains a lot of things about other elements on our periodic table. And that's the reason why the Bohr model of the atom is the most used model of the atom for all of high school and realistically like the start of university as well. So you deal with the Bohr model a ton. So let's jump into it. This is what you probably know from Chem 20 or Science 10, or depending on what chem courses you've taken. Bohr was the first model to introduce quantum theory, or sorry, first person to introduce quantum theory to the atomic model. Now what he did, right, was he said that the energy levels are all quantized. So you might remember, let me go back here. You might remember the idea of energy levels and the fact that there are 2 electrons typically hang out, or up to 2 hang out in the first energy level, up to 8 hang out in the second energy level, up to 8 in the third, and then it gets a little bit trickier after that. But that's sort of what we've learned about the Bohr model. And when we say quantized, we're talking about those energy levels. So they're very, very specific energy levels. And again, he made this to explain the emission and absorption spectra for hydrogen. So here is the emission and absorption spectra for hydrogen. You notice we've got purple, we've got blue, we've got green, and we've got red, and that's all there really is in the visible spectrum. So Bohr was really curious why hydrogen makes these 4 visible lines and no others. None, not a single one. So again, the orbital radii are quantized. I kind of got ahead of myself a second ago there. So here is our model of hydrogen. So you know hydrogen has an atomic number of 1. That means that it's 1 proton. And if we're talking about hydrogen atom, that means it's electrically neutral, so it's also 1 single electron. So here's our proton inside of the nucleus. Very, very nice. And here's our 1 electron. And what we've talked about in every other course so far is that electrons like to fill up from the inner orbitals to the outer orbitals. Orbitals, remember, are just spaces where electrons could be. Doesn't necessarily mean it's where they are. So we've always talked about, okay, well, it's 1 electron's going to go in its first orbital or inside energy level. Cool. That doesn't mean that there are not other orbitals. So first orbital, second orbital, third orbital. There are other orbitals there. It's just the lowest energy state is at its ground state, which is in that first orbital that we've got right there, and that's where it usually is. But that electron can jump back and forth between the different energy levels, and that's sort of what we're exploring for today. So what Bohr looked at is those energy levels are not only quantized, but they have very, very, very extremely specific energies that correspond to those orbitals. So this is a little bit weird to look at first, but it kind of makes sense once we start to go through. So first and foremost, we're typically talking about like electric potential energy or photon energy. So electric potential energy, when we're thinking about this electron, it has the most electric potential energy when it's furthest away, and then the closer it gets to where it wants to be, right next to that proton, the less it has. So our diagram that's a little bit tricky over here is at its first orbital, or lowest energy, it's got negative 13.6 electron volts. Now this is very specific for hydrogen as well. We're all talking about hydrogen here. At its second energy level, it's got negative 3.4, negative 1.5, negative 0.85. There's a whole bunch of other ones in here, and then 0 electron volts. Very weird, very interesting. We start at 0, and then the closer it goes, it is less electric potential energy. For example, negative 3.4 is less than 0, and negative 13.6 is less than negative 3.4. But we're kind of working with these negative numbers, which is kind of strange. So what physicists have done is, for the most part, they say when that electron is not at all associated with the atom anymore, so it's out there in space, it's not at all attracted to that proton, whatsoever anymore. That's what we call 0 electron volts, right? So there's no connection whatsoever. And then if we were to get closer, well, it would have less energy, so it would have less than 0. So it's negative. So I hope that kind of makes sense for people. The other way that we can think about that is in order to get to n is equal to infinity, we need the ionization energy. Because what is ionization? Well, that's when an electron gets kicked out and we're left with a charged particle or an ion. In this case, there really is only one electron, so we're left with just a proton and there's nothing else. Now, the ionization energy is the minimum energy needed to remove it. So when I'm thinking about this, I have to get my electron from negative 13.6 electron volts all the way up to 0. It needs to gain 13.6 electron volts in order to get there, 13.6 electron volts to be ionized. Cool, so kicked out, in other words. All right, one thing that we can look at with this, it's taking a bit of a left-hand turn here, but it's still something we need to know, is, well, I've got my proton and I've got my electron, and my electron is in circular motion around my proton. It's actually kind of an orbital motion, right? And if we look back to physics 20, orbital motion is where we've got, in circular motion, our velocity is always tangent to the circle. It's not a very good tangent, but that's fine. The acceleration, I'm going to call it centripetal acceleration because it's going around in a circle. It's causing it to deflect the velocity but not increase or decrease it. So our acceleration is towards the center. Therefore, our net force must also be towards the center. What is our net force actually made of in this case? So remembering that net force and Fc are the same thing, well, the net force is the electric force. That is what's attracting the electron to the proton. So we can actually go through and we can say, oh, okay, well, if I'm going through and checking this out, well, this is just m times ac, so net force is mass times acceleration, so Fc is mass times centripetal acceleration. And then my electric force, well, this is between 2 point charges, so we go all the way back to unit 2, K1 Q2 over r squared. So the electric force between 2 point charges. Cool. I can expand on this even a little bit more. I might say something like mv squared divided by r, because remember ac is v squared over r, and I might be dealing with the orbital speed of that radius or something, right? You know, for a question that's coming up in a second. And then, well, if I think about the charges on Q1, and I wrote Q1 twice, Q1 and Q2, well, it's a proton and electron. The magnitude of those are exactly the same, so we can say Q squared over r squared. And then, of course, we see one of the radius cancel. And now we've got a formula where we could solve for, say, the orbital speed. Hey, check this out. An electron orbits Bohr's hydrogen atom with a radius of 4.6 times 10 to the negative 10 meters. Determine the orbital speed. Go figure. Hey, we got an example just like that. So this is physics principle 2. What I'm going to get you to do, we just kind of went through the math for this, so I'm going to get you to put the video on pause. I'm going to get you to try it out. When you're ready, unpause, and I will have the answer ready to go as well. I'm also going to put it on pause. So go ahead and do that right now. Alrighty, so I've got my answer up here using physics principle 2, starting off with, let's see, I'm going to use a different color to highlight here. Starting off with Fc, that's the sum of all forces. All we've really got here is Fe. So I went and I expanded. Fc is mv squared over r, or in other words, it's m times ac. And then Fe is k q1 q2 over r squared, but I realized that q1 and q2 are exactly the same. So rather than doing q1 times q2, I just said q squared. We rearrange to get V all by itself, so just double check your rearranging. One thing that some people might have been a little bit confused about is, well, I guess two things actually, is when we're using our charges, anytime we did this, we had magnitude only in pretty much every formula from Unit 2. All directions came from diagrams. So magnitude only. And then the other thing is, which mass do we use? Right? Which mass? Well, I'm talking about circular motion over here, right? Circular motion. Which is going in circular motion? Is it the electron or the proton? It is the mass of the electron that was actually going in circular motion. So we see the mass of the electron over here. And when we plug all numbers in, remembering to square and square root and all of those very important things, we end up with 7.29 times 10 to the power of 5 meters per second, which is reasonable for an electron. It's ridiculously fast, but it's also an electron. We've seen huge, huge, huge values for the speed of electron. Cool. So hopefully that's good for people. We haven't really explained the emission or absorption spectra yet, so that's what we kind of got to work on next. Let me get back to the nicer felt pen. Yeah, there we go. So emission and absorption spectra and these quantized orbital radii. That's our next big goal. So the whole thing is, just like when we were talking at the very beginning of this unit, it's all about jumps between energy levels. So if it's jumping from a higher energy level to a lower energy level, well, that extra energy's got to go somewhere. You probably guess it. It's going to be given off in terms of a photon. Perfect. And we can treat this in terms of conservation of energy. ETI equals ETF. So I'm starting with the energy at the upper level, which I'm going to call EU. And I end up with some photon energy plus my energy at the lower level. Cool, okay. We kind of like to focus on that photon energy. So the photon energy is my upper level minus the energy at the lower level. Perfect. Remember this. Remember this. Let's check it out for the other side of things. Right, so let's see. Emitting photons, we're going from higher energy to lower energy levels. If we are absorbing photons, let's check this out for a quick second. You can ignore that for the time being. If we're absorbing photons, now I've got this photon coming in, it's interacting with that electron, it's getting absorbed by that electron, and it's pushing it up to a higher energy level. Let's just check this out for a quick second. Same thing, conservation of energy. We are starting off, in this case, with the energy of the photon, plus whatever energy that electron's got at the lower level, and that's going to be equal to the energy at the upper level. Cool. Again, let's focus on the photon energy. It's going to be our upper level minus the energy of the electron at the lower level. Hey, that's the exact same thing that we just talked about. So long story short here, it doesn't matter if it's emitting or absorbing. You should just know this formula. I just memorized that formula. The energy of the photon is equal to the energy of the electron at the upper level minus the energy of the electron at the lower level. It will be absorbing photons if it's jumping up to higher energy levels, like we've got here, and it will be emitting photons if it's going from higher to lower, like we've got on the previous slide here. Cool, I hope that makes sense for us. So what we look at with this is, and this really starts to help explain the emission and absorption spectra, because if I've got a difference in energy levels between my lower and my upper energy level here of 6 electron volts, well, that means if it falls down, it's going to emit a photon with an energy of 6 electron volts and a corresponding wavelength and frequency for 6 electron volts. If it's exactly 6 electron volts to go from the lower level to the upper level now, it can absorb photons with exactly 6 electron volts, and it can go up to higher energy levels, right? So when it is emitting, so our emission spectra that we've got right here, here's our emission spectra. This is all about electrons falling from a higher energy level to a lower energy level. When I've got my absorption spectra, it's all about them going and absorbing photons going from a lower energy to a higher. So if it's emitting photons, you see light. If it's absorbing photons, it's taking that light. Cool. Very, very cool. One thing to notice with this that'll come up in a little bit here, one thing to notice is that it's the exact, and in the Bohr model, it is the exact right amount of energy for photons. So we don't have like, oh yeah, okay, sort of some photons here, but then they change into yellow. No, that does not happen. It has to be the exact right amount of photon energy that is either being released or being absorbed. There's nothing in between. Cool. So let's check this out. Let's do a quick example here. We've got the total energy of an orbiting electron is negative 7.15 electron volts. Nice. It then emits a 260 nanometer photon. Awesome. Determine its total energy after the emission. So something that's really, really important here that I didn't underline yet is it is emitting a photon. So what that means is it's starting at its upper energy level, which would be 7.15 negative, sorry, 7.15 electron volts. And if it is emitting a photon, that means that it is falling to a lower energy level, right? So we've got the upper, it's falling to a lower, and we also have enough information to figure out the energy of that photon because we have the wavelength of that photon. So let's go through. We know the energy of the photon is always equal to our upper energy level minus our lower energy level for the electron. We are looking for the lower energy level. So I just need to rearrange. That's my photon energy. Oh, I got this a little bit backwards here. This rearranging is a little bit trickier than I thought. So lower energy level, it's negative. What I'm going to do is I'm going to add that to this side, and then I'm going to subtract the photon energy from that side. That'll be a little bit easier. That way I end up with my lower energy level as a positive number, not negative, and then it would be a negative negative, which would get confusing and annoying. So my energy at the lower energy level is going to be my energy at the upper minus the energy of the photon. And that makes sense, right? Because my upper level is like my total amount of energy. The lower plus the photon must be equal to the upper. So find the difference between the highest and the photon, we'll get the lowest energy level. So my upper energy level, well, that's just negative 7.15 electron volts. That's no problem. And actually, you know what? I'm not going to plug numbers in quite yet. I'm going to say energy upper, because I really want to deal with that energy of the photon still. How do I calculate the energy of a photon? Well, it's either equal to h times f or hc over lambda. I'm given the wavelength, so I think I'm going to use hc over lambda for this one. That makes a lot more sense to me. Okay, so now we can start plugging in numbers. Negative 7.15 electron volts. I want to subtract from this Planck's constant. Now we got two versions. I'm dealing with electron volts. I probably want everything to be in electron volts, so I'm going to use the 4.14 times 10 to the negative 15 electron volt seconds times the speed of light, 3 times 10 to the power of 8 meters per second, and then divided by the wavelength. What was it there? 280 nanometers? Nope, 260 nanometers. So 260 times 10 to the negative 9 meters. So subtracting this whole piece, put some big brackets around it. Take a moment to plug in some numbers. I end up with negative 11.9 electron volts. And I know that that makes sense because it is less than negative 7.15 electron volts. Negative 11 is less than negative 7. That makes sense. Cool. Now we could have done this in two steps. Like if you wanted to figure out the energy of the photon all by itself and then subtract the two, that's absolutely no problem. But yeah, be familiar. It's always energy of the photon is upper minus lower, and then lots of times you'll have to solve for the lower energy level. Lots of times you have to solve for the upper energy level. And also keep in mind, emitting versus absorbing tells us different things about the question. Cool. Okay. So one more example, and this comes back to the idea that photons need exact right energy. So photons, if they're going to be absorbed, they need exactly the right energy to land them exactly perfectly on an actual energy level. Right? So they can't, an electron can't I can't talk here. An electron can't land somewhere between n is equal to 2 and n is equal to 3. It has to be exactly n is equal to 2 or exactly n is equal to 3. So please keep that in mind. So we've got a fictional 1 electron atom, and we need a fictional 1 electron atom because we would get tired of dealing with hydrogen otherwise. Hydrogen's the only atom that really only has 1 electron, and this math really only works out for 1 electron atoms. Anyways, it's initially unexcited. Initially unexcited. That means that our electron is hanging out down here at n is equal to 1. We want to describe what happens when it receives the following low energy photons. So 8 electron volts, 10 electron volts, and 20 electron volts. So what happens when those 3 photons come in and they hit and interact with that electron? Does it jump up to a higher energy level? Does it stay where it is? Does it get ionized? Let's find out, keeping in mind that it has to be the exact right amount of energy to get to a higher energy level. So let's start with the 8 electron volt photon. So I know the energy of the photon is my upper energy level minus my lower energy level. I'm focusing on my upper energy level because if it lands it on an exact energy level, it will be absorbed and it'll jump up there. So upper is going to be equal to the photon energy plus the energy at that lower level. Now this, we're going to use this on every single example, so we'll just kind of keep that in mind. We've rearranged it once, we don't need to rearrange it every time. So I got 8 electron volts plus my lower energy level is negative 17 electron volts. So 8 plus negative 17, well that there is negative 9 electron volts. So is that a real energy level, an actual energy level? It is, and because it's a real energy level, that upper level is an actual real one that corresponds to this, this will absorb the photon, and the electron will go from n is equal to 1 to n is equal to 2. Cool, because again, it's a real energy level. Nice, okay, let's check out the next one here. Now we've got this 10 electron volt. So it starts from here. Is that going to take me up somewhere higher? So we've got the energy at the upper level is equal to the energy of the photon plus the energy at the lower level. That's what we rearranged in the last example, remember? So now I've got 10 electron volts plus negative 17 electron volts. Well, that's just negative 7 electron volts. So let's see. Lots of people would say it was going to jump up to here. Well, there's nothing there. So it's, how can it jump up if nothing's there? That doesn't correspond to an energy level. So back to the old felt pen there. This doesn't correspond to a real energy level. So the photon is not even going to be absorbed. So photon not absorbed, and the electron stays at n equals 1. So if it's not the right energy, it doesn't go anywhere. Okay, there are always some exceptions to the rules, so let's check out the next one. Oh, what the heck is this? It's a typo, that's what it is. That should say 20 electron volts. I got it wrong up top, but right down at the bottom. So now 20 electron volts. Okay, so let's figure this one a little bit here. I have got my energy at the upper level, it's my photon energy plus my energy at the lower. Getting a little bit redundant, but it's nice to have that for every single one. So now I've got 20 electron volts plus negative 17 electron volts. Hey, that's positive 3 electron volts. That's higher than our ionization energy, or n is equal to infinity, when the electron's not even there. So when I look at this one, well, it doesn't match one of the specific ones perfectly. Is that enough energy to totally kick out that electron? That is. This is beyond, how am I going to word this? This is beyond n equals to infinity. So the atom will be ionized. So it takes 17 electron volts to get it up to ionization energy. Any guesses what's going to happen with those 3 extra electron volts of energy? If you're thinking kinetic, you're spot on. And the electron will be kicked out with 3 electron volts of kinetic energy. Nice. So it's got more than enough to separate that electron from its atom, or from its nucleus, and anything that's left over is going to go into kinetic energy. Perfect. Okay. So we still haven't necessarily explained why we have those very, very specific emission and absorption spectra, although I'm sure a few of you are starting to guess it and to get the ideas, right, the big, big, big ideas. So we're going to start with the emission spectra. Remember, emission spectra can be created when we have a low pressure gas that is excited by running current or running electrons through it. So one of the things that we've talked about so far is the visible light. Yeah, we've got violet, blue, green, and red, but there is UV light given off, and there is IR light given off, or EMR at least, that's given off. It's just we can't really see that with our eyes, right? We need other instruments to check that out. So the first step is we need to excite those hydrogen atoms. So we are using free electrons, that's from our current, that are smashing into the electrons below. They are causing them to be excited up to higher energy levels. Realistically, depending on how much of this free electron's energy is given off, it could go up to any energy level. I think the example that we look at, though, goes up to energy level 5. I kind of drew that a little bit funky there. So could go up to any energy level, depending on how much energy is given off. So we talked about with a photon is all or none for energy, right? There's no in-between ground. But could an electron give off part of its energy? Absolutely, because it's just kinetic energy that that electron's got. So we might kick it up to n is equal to 5. Nice. Now let's think about how that electron could get back down to n is equal to 1, our first energy level. Well, it could just drop all the way straight down. Or it could take a little break at n is equal to 4, n is equal to 3, n is equal to 2, and then is equal to 1. Or it could go from 5 to 3 and then 3 to 1. Or it could go from 5 to 2 and then 2 to 1. There's many, many, many different paths that that electron could take. And remember, when we have this low pressure hydrogen gas that's being excited, there's probably more like billions of these electrons all doing this at the same time. So billions of electrons all doing the same thing at the same time. We kind of focus on just one of them, but remember they happen like over and over and over again with them. So this emission spectra, this is a bit of a confusing diagram at first, but this emission spectra tells us a couple things. Let's start with the UV at the top here. So any drops down to n is equal to 1, so any of these drops are going to give off UV radiation, right? It's the biggest jump, it's the biggest change in energy, and the biggest change of energy that we see corresponds to the highest energy of photons, which is UV, right? And even going back, let's see, I don't know where I'm going with this actually, there we go. Even going back to here, the jump between n is equal to 1 and n is equal to 2 is big. It's 10.2 electron volts. And then after that, it's like about 1.5, about 0.7 or so, about 0.3, and so on and so on. So the biggest jump, which corresponds to the biggest energy, is always dealing with n is equal to 1. That's UV. Visible is kind of middle of the road, and all the visible light are jumps between higher energy levels down to number 2 for emission. So our second orbital. Now you could probably guess with this, like which one has the highest energy? Violet. So violet is going to be the biggest jump, then blue, second biggest, then green, and then red. And then finally, the infrared, well, this is pretty much anything above n is equal to 3. So jumps to n is equal to 3, jumps to n is equal to 4, jumps to n is equal to 5. All of those tiny little jumps, they correspond to tiny little amounts of energy, which correspond to infrared. So that was a lot, and that was quick. Let's slow it down a little bit. The visible lines. Remember, the visible lines, the lower level is always n is equal to 2. So when we're emitting, we're always dropping down to n is equal to 2. So the lowest energy photon is red. It's going to have the lowest energy jump down to orbital 2. The lowest energy jump is from 3 to 2. Perfect. Cool, cool. If we wanted to predict the actual wavelength of that, well, we just use our energy of the photon is equal to energy upper minus energy lower, and we could actually solve for the wavelength of that light, and it does correspond to those energy levels, which is cool, awesome. The other ones are sort of the same idea. So the next largest amount of energy is green, or the next least, I guess I should say, is green. That's from 4 to 2. Then we've got blue, a little bit more energy, a little bit bigger of a jump, 5 to 2. And then finally violet, the biggest in terms of visible, biggest energy and biggest jump. So that's from 6 down to 2. Cool. So again, for visible light, the lower level is always 2, and the upper level is 3, 4, 5, or 6. And you need to know whether it's red, green, blue, or violet for our upper level. What about the UV lines? So the whole key with this is the lower level is n is equal to 1, and it is a huge jump. Realistically, anything down to levels equal to 1 is going to give off UV because of this massive, massive, massive first jump, that first huge transition. Excuse me. The IR lines are kind of similar, right? So anything 3 and above, doesn't matter if it's from there to there, there to there, there to there, there to there, they're all tiny little jumps in energy, right? Tiny, tiny, tiny little jumps in energy, which correspond to relatively tiny anyways, which correspond to significantly smaller amounts of photon energy, which correspond to longer wavelengths or lower frequencies, which is IR or infrared. So nice, there we go, there we go. Nice little picture of that there. Smallest energy transitions, lowest amount of energy. So the summary, when our lower level is 1, we've got UV. When our lower level is 2, we've got visible, and we know we've got green, nope, red, green, blue, and violet, depending on the energy level. And when our lower energy level is 3, 4, 5, it's all about the infrared radiation, all about the infrared. Okay, so just as a quick activity, see if you can figure this one out. You can put it on pause. Maybe I'll do the same actually. And see if you can figure out these 3 jumps for this 1 electron. So it starts at n is equal to 5, then it jumps down to 4, then it jumps down to 2, and then it jumps down to 1. Which types of EM are emitted? Go ahead, put it on pause right now. Cool, so we're back. So 5 to 4, that's tiny, that's IR, no problem. 4 to 2, well, we know the lower level 2, that corresponds to visible, 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 but it's from the 4th, so it's not just any visible, it's green, and it's visible. And then 2 to 1, that's our biggest jump, that is UV. So hopefully people are agreeing with me there. Okay, and this is just some space for me to work. Explaining our absorption spectra now. Well, pretty much the exact opposite, right? So we've got a hot, dense object, gives off all frequencies, goes through a low pressure unexcited gas, and then we see these dark missing bands, these dark, dark, dark missing bands. So originally, if our hydrogen ion is unexcited, that means the electron has to be in n is equal to 1. What type of radiation do we need in order to see this absorption spectra? You absolutely 100% need some form of UV. If you do not have UV radiation, it's not going to have enough energy to jump up to n is equal to 2 or 3 or 4 or 5 or 6. It has to have UV, and it has to have a minimum amount of energy, 10.2 electron volts, to make it jump up to n is equal to 2. Minimum amount of energy. Cool. Yep, so that's pretty much saying the same thing. Again, needs a UV as an absolute minimum to get it up there. Once we get that, so there's our UV, there's our minimum amount of energy. After that, once it gets to n is equal to 2, it can start to absorb red. And if it absorbs red, it goes from 2 to 3. It could absorb green. Okay, that's not what I'm looking for. It could absorb green. Hey, go back, go back. Okay, I'm all over the place here. It could absorb green. And if it absorbs green, it's going to go from 2 to 4. It could absorb blue. If it absorbs blue, it's going to go from 2 to 5. It could also absorb purple, which was my original color that I was working with. And if it absorbs purple, it's going to go from 2 all the way up to 6. And so on and so on. Actually, here's another question for you. This is a bit of a trick for you, though. What if it goes up to n is equal to 7? So from 2 to 7. Technically, it would need something with more energy than violet You guessed it, another ultraviolet, which we don't really talk about too much, but you might see every now and again. Cool. So similar stuff happens for all the products. So let's just do this quick activity together. Determine the transition for the Bohr model of hydrogen. So we're looking for, actually, you know what? I'll get you to put it on pause, and then we'll compare answers in a second here. We'll just go ahead and put it on pause right now. Alrighty, so I've got my answers up here. Emission of violet, that means it's going from higher to lower, so in this case 6 to 2. Absorption of green, it's got to be going from a lower energy level to a higher, so in this case from 2 up to 4. Question 2, determine the type of EMR emitted or absorbed. So I like to write down whether it's emitted or absorbed. So from n to 1 is 5, that's UV radiation absorbed. From n is equal to infinity to n is equal to 4. It's a bit of a tough one, that n is equal to infinity. My best answer, I think, would be IR, but it kind of depends on how much energy the electron had beforehand. I would just go with IR, though, right? Anything above 3. Okay, that's some space to show our work. Last thing to talk about here is evaluating the Bohr model. So when I go through and I evaluate the Bohr model, and when we look at this, well, Bohr did a great job, like a fantastic job, of figuring out all the lines for hydrogen's emission and absorption spectra, which is awesome. It works super good for any other atoms that only have one electron. How many atoms only have one electron, though? So it pretty much worked well for one atom that's pretty dang common, and then like a helium-1 plus almost never happens, so really not that useful in the grand scheme of things for that. Very useful for chemistry, I'll give you that, right? We use the Bohr model all the time, but as far as the emission absorption spectrum go, it's great for hydrogen, right? Everything else, not so much. It could not explain sodium, helium, neon, mercury, any other atom. It could not explain why only certain orbitals are allowed. So it says that they are allowed. The math checks out for hydrogen, but why are only certain orbitals allowed? Totally up in the air there. It could not explain, and this is still one of the problems we had with the Rutherford model, shouldn't those electrons, if they're whizzing around in circular motion, shouldn't they be emitting EMR? And shouldn't that EMR take up some energy? And then if it's losing energy, shouldn't that electron spiral into the nucleus real quick? That's not happening. And then also it could not explain why some lines are brighter than others. So I wish I could show you this in class, but here's a couple others, like a couple things that other scientists have put together. So, you know, when we're looking at the sun, we get this massively bright red line, and then this very, very, very dim violet line, right? Massively bright yellow and red, and then super dim violet. Like, why are some of them brighter than others? The answer to all these questions lies in the next lesson. I'll see you there. Bye for now, Physics 30s. It's been fun.